Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Gilbert Newton-Lewis 1946 paper, Valence and the Structure of Atoms and Molecules, stands as a pivotal, precocious, and paradigm-shifting contribution to the nascent field of chemical bonding. Its significance resides not only in its specific proposals regarding atomic structure and valence but, perhaps more importantly, in the conceptual frameworks it introduced, frameworks destined to profoundly shape the trajectory of theoretical chemistry throughout the 20th century. This essay will explore the genesis of Lewis' ideas, the core tenets of his 1946 paper, its reception within the scientific community, and its subsequent influence on the development of chemical bonding theory. The intellectual landscape preceding Lewis' 1906 publication was a complex tapestry woven from threads of classical physics, early atomic models, and the burgeoning field of chemical thermodynamics. John Dalton's atomic theory, proposed in the early 19th century, had provided a foundational framework for understanding chemical reactions in terms of discrete, indivisible atoms. The discovery of the electron by J. Thomson in 1897 challenged this notion of indivisibility, revealing a subatomic particle that inevitably became viewed as a fundamental constituent of all matter. Thomson's plum pudding model, which envisioned electrons embedded within a sphere of positive charge, represented an initial attempt to reconcile the existence of electrons with the observed neutrality of atoms. However, this model failed to account for the stability of atoms or to explain the specific combining ratios observed in chemical compounds. Concurrent with these developments in atomic physics, chemists were grappling with the concept of valence, the capacity of an atom to combine with other atoms. Edward Frankland's pioneering work on organometallic compounds in the mid-19th century had led him to propose that elements possess a definite saturating power, a fixed capacity, to bond with a certain number of other atoms. This idea was further developed by Archibald Scott Cooper and Auguste Kekulé, who independently introduced the concept of chemical structure, representing molecules as networks of atoms linked by valence bonds. These structural formulas successfully explained isomerism, the existence of compounds with the same elemental composition but different properties, by postulating different arrangements of atoms within the molecule. It is intriguing to note that while structural formulas were immensely useful in predicting and explaining chemical behavior, they lacked a firm theoretical foundation, relying on empirical observations rather than a fundamental understanding of the forces holding atoms together. Lewis' genius lay in his ability to synthesize these disparate threads into a coherent and compelling picture of chemical bonding. In his 1906 paper, he proposed that valence was related to the number of cubical positions that an atom possessed on its outer shell. He envisioned the atom as having a cubic structure, with electrons occupying the corners of the cube. Each corner represented a potential bonding site, giving each atom a valence of up to 8. He surmised that atoms tended to a little configuration with a full complement of outer electrons, a concept that would later be formalized as the octet Lewis cubical atom model, while ultimately incorrect in its geometric details, represented a significant departure from previous conceptions of valence. Instead of viewing valence as an intrinsic property of an atom, he proposed that it arose from the atom's tendency to achieve a stable electronic configuration. This concept provided a unifying framework for understanding both ionic and covalent bonding. In ionic bonding, atoms would transfer electrons to achieve a complete octet, resulting in the formation of charged ions that were attracted to each other by electrostatic forces. In covalent bonding, atoms would share electrons to achieve a complete octet, resulting in the formation of a shared electron pair that held the atoms together. One particularly insightful aspect of Lewis' 1906 paper was his emphasis on the role of electron pairs in chemical bonding. He recognized that the shared electron pair represented the fundamental unit of the covalent bond, a concept that would later be rigorously justified by quantum mechanical calculations. This emphasis on electron pairs also provided a natural explanation for the tetravalence of carbon, a cornerstone of organic chemistry. Lewis proposed that carbon could form 4 covalent bonds by sharing 4 pairs of electrons with other atoms, resulting in a stable octet configuration. The reception of Lewis' 1906 paper within the scientific community was mixed. Some, like Thomson, were deeply skeptical of atomic models in general, viewing them as little more than speculative constructs. Others, particularly those working in the field of chemical thermodynamics, were more receptive to Lewis' ideas, recognizing their potential to explain the observed energetic stabilities of chemical compounds. However, the cubical atom model also faced significant criticism. The assumption of a static, cubic structure for atoms appeared inconsistent with the known properties of atomic spectra, which suggested that electrons were in constant motion. Furthermore, the cubical model struggled to account for the bonding in molecules with odd numbers of electrons, such as nitric oxide, and for elements beyond the second row of the periodic table, where the octet rule was frequently violated. Despite these limitations, Lewis' 19-6 paper laid the groundwork for his more fully developed theory of chemical bonding, which he presented in his seminal 19-16 paper, The Atom and the Molecule. In this later work, Lewis abandoned the cubical atom model in favour of a more abstract representation of the atom as a kernel surrounded by a valence shell of electrons. He retained his emphasis on the importance of electron pairs in chemical bonding, introducing the now familiar Lewis dot structures to represent the valence electrons of atoms and molecules. Lewis' 19-16 paper also provided a more refined explanation for the octet rule, relating it to the tendency of atoms to achieve the stable electronic configuration of a noble gas. The impact of Lewis' work on the development of chemical bonding theory was profound. His ideas provided a conceptual framework for understanding the nature of the chemical bond, paving the way for the development of more sophisticated quantum mechanical theories of bonding, such as valence bond theory and molecular orbital theory. Linus Pauling, building upon Lewis' ideas, developed valence bond theory, which explained chemical bonding in terms of the overlap of atomic orbitals. Friedrich Hund and Robert Mulliken developed molecular orbital theory, which described chemical bonding in terms of the formation of molecular orbitals that were delocalized over the entire molecule. Both valence bond theory and molecular orbital theory, while differing in their mathematical formalism, owe a significant intellectual debt to Lewis' pioneering work. Furthermore, Lewis' emphasis on the importance of electron pairs in chemical bonding had a lasting impact on the way chemists think about molecules. The Lewis dot structure, introduced in his 19-16 paper, remains an indispensable tool for visualizing the electronic structure of molecules and for predicting their reactivity. The concept of the electron pair also played a crucial role in the development of the theory of acids and bases. Lewis proposed a generalized definition of acids and bases, based on their ability to accept or donate electron pairs, a definition that broadened the scope of acid-base chemistry and provided a more fundamental understanding of acid-base reactions. In conclusion, Gilbert Newton-Lewis' 19-6 paper, Valence and the Structure of Atoms and Molecules, represents a landmark achievement in the history of chemical bonding theory. While his cubical atom model proved to be an ultimately flawed representation of atomic structure, the paper introduced a number of groundbreaking concepts that would profoundly influence the development of theoretical chemistry. His emphasis on the role of valence electrons in chemical bonding, his recognition of the importance of electron pairs, and his proposal that atoms tend to achieve a stable octet configuration laid the foundation for our modern understanding of the chemical bond. Lewis' work, initially met with some skepticism, ultimately revolutionized the field, providing chemists with a powerful and intuitive framework for understanding the structure, properties, and reactivity of molecules. His legacy perseveres, not merely as a historical footnote, but as an integral cornerstone of modern chemical thought. The seeds he sowed in 1906 continue to blossom in the fertile soil of contemporary scientific inquiry.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.